space, and matter. Now see further than we've ever imagined, beyond the limits of our existence, in a place we call the universe. Chaotic and breathtaking, their beauty forms from the emptiness of space.
Nebulas are everything in the galaxy that stars are not.
Wisps of matter, at times coming together, at others flying apart. Filmy veils, billowing masses, some dark, some glowing in brilliant colors, many taking the shapes of things that are eerily familiar.
It's interesting when people look at nebulas, they sort of start seeing things in it.
Neither stars nor planets, they are the crown jewels of the galaxy. The universe reveals its awesome display of stellar birth, death, and the cycle of creation inside the nebulas. It is one of the most famous space photographs ever taken. As seen by the Hubble Space Telescope, it shows the pillars of creation. Massive columns of dust and gas 7 light-years long. As big as they are, the pillars are just a small part of an immense stellar nursery 6,500 light-years from Earth, called the Eagle Nebula. Nebulas of all kinds are scattered among the stars everywhere and are among the most spectacular sights in ours or any galaxy.
Nebulae are beautiful, all of them. They really strike the eye.
From the Greek word for cloud, nebulas are just that. Clouds of interstellar gas and dust, rarely visible to the naked eye. But with telescopes in space and on Earth, their beauty is revealed. Glowing, reflecting, or obscuring the galaxy's light. They are regions where stars are born, where stars die, and where explosions rack the very fabric of space-time.
Nebulas have fantastic shapes, like clouds in the sky on a summer day. They often evoke imagery that hits very close to home. Images of flowers, images of insects, images of people.
It's interesting when people look at nebula, it's like a Rorschach test. They sort of start seeing things in it.
Although nebulas are labeled with numbers from astronomical catalogs, many also have names inspired by their locations or shapes. It's not difficult, for instance, to see why this is called the Butterfly Nebula, or this is known as the Horsehead Nebula. The list goes on.
The Orion Nebula, the Ghost Head Nebula, the Stingray Nebula, the Helix Nebula, the Cat's Eye Nebula, the North American Nebula, the Pelican Nebula.
The astonishing forms nebulas take make them the tourist attractions of the galaxy.
If you've got the family in a flying saucer and you're careening through the Milky Way looking for an interesting rest stop, you're going to go to a nebula.
Like tourist attractions on Earth, faraway nebulas entice us for a closer look.
Man, it's a hike.
One of the prime attractions in the night sky is the Great Orion Nebula. One of the very few nebulas you can see with the naked eye. On a clear night, it appears as a fuzzy star in the Sword of Orion. Probably the most recognizable constellation in the sky.
The Orion Nebula is the most active area of star formation in our galaxy. It lights up the sky like nothing else. So this is a big one. In terms of nebulas, this is the Hollywood sign.
And the reason why travelers want to get close to tourist attractions is the same as why astronomers want a closer look at nebulas. They each want to take photos. After all, tourism, whether earthly or astronomical, is all about the pictures.
Photographs of nebulas occupy a real special niche, a very important niche, I think, because they really do sit at the pinnacle, the confluence of art and science.
Of course, getting good pictures of a nebula isn't just a matter of point and click. In the mountains north of San Diego, a group of amateur stargazers have an especially tough road to follow in seeking out nebulas and taking great pictures.
It is always worth the long drive to come out here. Night under the stars, even if I don't do any imaging, is worth it, just to see what I can't see from home.
When the equipment is this complex, these enthusiasts aren't just taking pictures. Here, the word is imaging. And their favorite targets are the nebulas.
Just being able to look at them and imagine what's going on out there in that gas cloud, being able to see a sense of where stars are forming, it's just a great kind of a sensory experience to have.
In addition to their portable telescopes, the group has also built a complex of permanent observatories. Inside the enclosure housing their big 20-inch telescope, accomplished astrophotographer Alan Smallbone attaches a special astro camera to the eyepiece. He's preparing to image the Orion Nebula.
It's a very challenging object to me because it has very light areas, it has very bright areas, it has very dark areas, and it's a very difficult item to photograph accurately.
The digital cameras used by today's astrophotographers emulate color vision in the human eye itself. There are 3 kinds of cone cells on the retina, each sensitive to either blue, green, or red light. That's why those colors are considered the primary colors of light. But the retina of an astro camera is a computer chip, sensitive only to black and white. So for color photos, it uses red, green, and blue filters, taking at least one shot with each one. It's often called the RGB technique and is standard for producing more natural color. In capturing the Orion Nebula, Smallbone takes time exposures lasting 5 minutes through each of the 3 filters. But nebulas are so dim that for the best photos, he often needs dozens of exposures, with times totaling as much as 14 hours. No one ever said this was easy.
Astroimaging can be very tedious because it's very time-consuming. It involves long periods of time where you're sitting waiting for the camera, and the mount is just tracking, and there's really nothing you can do except sit and wait.
Later, Smallbone stacks the raw images on his computer. There, the different combinations of red, blue, and green dots work just like a color TV to create every other hue in the spectrum. Hours after first opening the shutter, the Orion Nebula appears in its natural colors on the screen, as no human eye has the sensitivity to see it. The striking images of these and other nebulas demonstrate the essential reason astrophotography is indispensable when it comes to the nebulas.
The combination of a telescope and a camera actually allows you to see details and structures in the nebulae that you couldn't see with your own eye because they're so faint and diffuse.
The Great Orion Nebula is well worth the attention it gets. 15 light years across, it is a massive cloud made mostly of hydrogen. It is the quintessential example of the kind of nebula known as a star-forming region.
It is the cradle of the most massive stars that are born in our galaxy. And it is the closest example of that process to us. So when you look at the Great Orion Nebula, you're looking at stars being born.
Among the thousands of infant stars in the Orion Nebula, 4 of them dominate. The corners of a cluster called the trapezium for its trapezoidal shape. Massive and hot, they are responsible for the brilliant astronomical display.
The trapezium in the center of the Great Orion Nebula is what energizes. It's what makes it a nebula. If you didn't have the trapezium stars, it would be a dark cloud.
Radiation from the trapezium stars sculpts the surrounding gas and causes it to glow with emitted light. What would it be like to fly through the Orion Nebula in a spacecraft? It might look like this. A remarkably accurate supercomputer simulation based on detailed Hubble Space Telescope data and modeled by Vanderbilt University astronomer Robert Odell. Traveling into the gigantic cloud, we see the 4 bright trapezium stars, their 3D positions now clearly evident. Their intense energy has hollowed out the nebula's center. The trapezium stars are so bright that they would blind us to the rest of the nebula if our view screen were not enhanced to show us all the details. The dark globs scattered about called proplyds, or protoplanetary disks, are blankets of dust surrounding newly formed stars, forced into teardrop shapes by energetic stellar winds from the trapezium. One of them clearly shows a ring of debris orbiting its central star, strong evidence that a new system of planets is forming. Our route out of the Orion Nebula shows us the angle at which we see it from Earth. But at 1,300 light-years away, it shrinks to a minor smudge in our field of view. Imagine how it would look at only 4 light-years, the distance to the nearest star.
The Orion Nebula, if we were as close to the Orion Nebula as the nearest star is to us, it would be so bright that we wouldn't be aware of the dark sky. We wouldn't see the other stars. We would almost not be aware of other galaxies just because it would be so bright. Our whole world would be the Orion Nebula and the sun.
Fortunately, we live at a point in the galaxy where our telescopes and cameras can comb the heavens to shake loose the gems we call nebulas. There are 5 major kinds. Star-forming nebulas like Orion are called H2 regions. H2 describes the thin hydrogen excited by hot stars to emit light. In other places, there are reflection nebulas, where the bright stars have driven away the surrounding gas, leaving mostly dust to reflect starlight. Planetary nebulas are formed during the slow dying stages of ordinary stars and produce some of the most intriguing displays of shape and color in the galaxy. Supernova remnants are also leftovers from stellar deaths, but from massive stars which end their lives in immense explosions. And finally, there are the dark nebulas, clouds of interstellar gas and dust, visible usually because they appear in silhouette against the bright nebulas behind them. In time, stars will burst into existence within them. But the very origin of the galaxy's clouds of stars, gas, and dust is the most intriguing phenomenon of all. Springing from the mysterious interstellar medium, the riddle of the nebulas is how they can form from what is almost nothing at all. Space and its vast emptiness has much more to it than meets the eye. Filling the distances between the sun and all its galactic neighbors is the neutral interstellar medium, or ISM.
When we think about the blackness between stars, we sometimes think there's nothing there but the vacuum of space. But actually, even the so-called vacuum of space is full of dust and gas. Now, it's quite rarefied. How rarefied? Perhaps better than the best vacuum we can create on the planet Earth.
The particles in the interstellar medium are 90% hydrogen atoms, 10% helium, and trace amounts of other elements and tiny specks of dust. Existence of the gas and dust is evident by looking at the Milky Way, the band of stars we see in the edge-on view of our home galaxy from Earth. There, the dark spaces seem to be empty, but in reality, the opposite is true.
Those spaces aren't devoid of stars. They're actually dust between us and the distant stars in the plane of our galaxy, and they block that light. And you see them in silhouette.
The black lanes of gas and dust show us where the interstellar medium is clumping together to form nebulas in their most primeval form. We see these dark nebulas as shadows against the background stars. The Snake Nebula is 650 light-years distant and approximately 3 light-years across. Even darker is Barnard 68, named for Edward Emerson Barnard, the astronomer who discovered it. Such nebulas may be deep enough to block light from stars behind them, but the gas and dust inside them is still very thin. That is, until gravity's work accelerates.
Gravity is attractive. As a consequence, we have lumps of gas, no matter how rarefied, being attracted by gravity until we have clumps of nuclear material condensing. As gravity begins to compress the gas, it starts to heat up in temperature, creating the temperatures of a star.
The new stars burst into existence, lighting up their surroundings with colorful brilliance. Remaining dark nebulas stand out in stark contrast. Like bright nebulas, their shapes suggest names. The Elephant's Trunk Nebula, the Cone Nebula, and the Flame Nebula, where dark and light areas create one of the sky's most dramatic images. The brilliant colors of the star-forming regions come from nebular gases excited by invisible ultraviolet radiation from nearby hot new stars.
The light, the ultraviolet light from those stars, is stripping off the electrons in the gas in its immediate vicinity. These electrons float around for days or weeks, and then ultimately find a bare proton or other positively charged nucleus. And they'll hop onto orbits, and as they do, they'll emit light.
At the University of Rochester, astronomer Adam Frank compares the excitement of gases in a nebula to a basketball game.
This basketball game is a real nice analogy, though earthbound, for what happens in a nebula. Down on the court, you've got Rochester going up against NYU. The basketball players are a lot like the stars at the center of a nebula. When something exciting happens on the court, you see the crowd getting all excited. The crowd stands up, they cheer, they emit energy. In this case, it's sound energy, but in the nebula, it would be light. This is exactly the same thing that happens when an electron gets ripped off an atom, flies around for a while, and then finds another atom to recombine with, and emits energy at the same time.
As new stars are born within the nebulas, they sometimes shoot out spectacular jets. This one is 3 trillion miles long. The jets are nebulas in their own right, generated by the orbiting cloud of gas and dust sending material into the young star.
Because of rotation, it first forms an accretion disk, which is kind of like a frisbee spinning around the young star, building the young star. Now, there's always magnetic fields in all of this gas, and as the disk spins, material loads up onto field lines, as we say, and it spins and then is flung out into space. Eventually, the field lines get bent around, collimating the jet, creating a nice solid jet column.
Along with stellar jets, the galaxy's nebulas display a wild variety of bubbles, shock waves, pillars, and even mountains. These are called the mountains of creation, a nebula often compared to the famous pillars of creation, but in fact, 10 times as large. Though they are 70 light years across, this image, taken in visible light, shows them subtle in appearance. But see what happens when we look at a picture from the Spitzer Space Telescope, which views them in infrared.
Infrared light is light of a slightly longer wavelength than visible light. It's redder than red light. We commonly see infrared light from objects like us that are warm but not extremely hot.
Since infrared light is emitted by anything that is warm, it's often used to detect heat. In special cameras, each temperature is detected as an infrared color that we can't see, and then it's translated into a visible color that we can see. That's how infrared can use body heat to reveal some amateur astronomers working in the dark of night, when otherwise we'd have to turn on a light to see them at all. In space, the same principle applies. This is the Eagle Nebula as seen in visible light. But the infrared Spitzer telescope sees it in a much different way, revealing a region of extremely hot dust, seen here in red.
Now you have to ask yourself, what could get dust that hot? The stars in the nebula, no, they're not really bright enough, they're not hot enough, but maybe a supernova explosion. Maybe the violent death of a star.
A supernova could send out a massive shock wave, which might have a profound impact because the Eagle Nebula is home to the pillars of creation.
Well, for the pillars, it doesn't look very good. What's going to happen is that supernova shock wave that's expanding out from the exploding star, sooner or later is going to hit those pillars. And when it hits the pillars, it's going to evaporate them and they're going to be destroyed, leaving the stars that are currently forming in the pillars behind. But all that gas and dust and those beautiful, pillar-like shapes, they're going to go just disappear.
The infrared that reveals the fate of the famous pillars is only one tool in the astronomer's light box. But the nebulas can be seen in light of all kinds, stripping away shrouds that keep their secrets otherwise hidden forever. In a universe filled with light, astronomers have learned to look at the stars by analyzing light of different kinds, such as the infrared images from the Spitzer Space Telescope. Infrared is only one region on the electromagnetic spectrum, an immense scale we use to measure the wavelengths of all kinds of radiation. At one end are radio waves with the longest wavelengths. At the other end are gamma rays with the shortest. In between are the other bands, including visible light, which is such a tiny fraction of the whole, it's difficult to imagine. How small is the visible spectrum? If you had a reel of movie film representing the entire electromagnetic spectrum, stretching 2,500 miles from California to Alaska, the section containing the visible spectrum would fall somewhere in the middle, near the University of Washington.
This frame is the whole visible spectrum. It is one frame in over 2,000 miles of tape, and it's everything that the human eye can see. The importance of this frame is that stars emit almost all of their light in this part of the spectrum.
And even though the light is visible, it still contains hidden tools, helping us to explore nebulas in ways that our eyes cannot do entirely on their own. The secrets are in the spectrum itself. The visible light in this lamp comes from hydrogen gas excited by electricity to form a glowing plasma, similar to what happens in a nebula. By viewing the lamp through a diffraction grating, we can split the light up into 3 narrow lines on the spectrum, a virtual fingerprint of light, unique to hydrogen alone.
So in the spectrum, you see 3 features. One is red, one is a light blue, and the other is a deep blue. This pattern of wavelengths is absolutely unique to hydrogen, and there's no way to confuse hydrogen in the spectrum of a nebula with any other element.
It's like the crowd at our basketball game. The cheering mass is actually made up of individual fans, each with his or her own distinctive voice. Voices you could make out clearly if you had a way to isolate them. Isolating the individual spectral lines of the elements within nebulas has allowed astronomers to create images truly worthy of these tourist attractions of our galaxy. By using what are called narrowband filters corresponding to single lines, astronomers have given us another way of seeing things we can't see by ourselves. When the Hubble telescope photographed the pillars of creation, it used one filter to isolate hydrogen's brightest red line, another to isolate sulfur's even redder line, and a third to capture oxygen's line of blue-green. Image specialist Zoltan Levay assembles the components into a full-color image that reveals more than the sum of its parts.
By taking images of a nebula through a filter that isolates the light of a particular element, we are seeing the distribution of that element throughout this nebula. But to a larger extent, we're seeing how the physical conditions vary across that nebula.
If the true colors of hydrogen, oxygen, and sulfur lines were combined, the image of the pillars would look something like this. But the Hubble team translates each element into one of light's primary colors. Oxygen's blue-green is assigned to blue, hydrogen's red is assigned to green, and sulfur, similar to hydrogen in color, is assigned to red. Sometimes called false color, the image is a better display of material reality.
This I would refer to as representative color, the way we've constructed this image. The colors may not appear the same as the colors we would see if we were looking at this with our unaided eyes or through a telescope, but they represent the physical processes that are happening here.
The hydrogen, oxygen, sulfur filters, as combined this way, are known as the Hubble palette, which is used widely in nebular photography of all kinds. It shows us not only the colorful chaos of star-forming nebulas, but also the striking images of the places where stars die. These beautiful, complex gems that dot the cosmos, marking the demise of stars, are called planetary nebulas, a term that was coined in 1784.
Planetary nebulae are objects that have nothing to do with planets, as it turns out. They get their name from William Herschel, who looked at a planetary nebula for the first time through a telescope, saw that it was round, greenish in color, and it reminded him of the planet Uranus.
The blue-greens of oxygen and reds of hydrogen dominate true color photos of planetary nebulas. The Ring Nebula is a prime example. It is 2,300 light-years from Earth and 1.3 light-years in diameter. It is considered a prototype for planetary nebulas. But the shape of the Ring Nebula is simple compared to other planetary nebulas. It's remarkable to realize that displays like these accompany the death of nearly every star in the cosmos, including our own sun in about 5 billion years.
The star swells up near the end of its life. The sun will fill half the sky. When the sun is setting in the west, another part of it will be rising in the east. And at noon, the whole sky will be filled with this bright red object, baking us to porcelain. At this point, the inside of the star becomes wildly unstable. It shudders and it quakes. And at that point, the surface, which is very loosely bound, can be tossed into space. Think of it as a process of stellar sneezing.
The outer envelope of gas expands as the sun shrinks from a red giant to become a hot white dwarf. The dwarf's ultraviolet light excites the surrounding gas, causing it to glow, just as in star-forming regions. The brilliant display will last for thousands of years before fading away. Just what kind of cosmic picture the sun will paint at the end of its life is nearly impossible to predict. But witness the astounding variety of planetary nebulas throughout the galaxy. What makes each one dazzlingly different? And what engines drive their enigmatic shapes? There are an estimated 10,000 planetary nebulas in our galaxy, each one displaying the death of a star in its own unique way. Although each planetary nebula is generated by a single star system, their size in comparison is immense.
Planetary nebulas are huge. If I had the solar system between my fingers, the planetary nebula would be 1,000 to 10,000 times larger in radius.
And yet, because of their great distance from Earth, most planetary nebulas appear to us as tiny specks in the cosmos. The distance to the planetary nebula NGC 2440 is 4,000 light years, and although the nebula itself is 1 full light year across, its size, when viewed from Earth, is only 4% as wide as the full moon. Only the most powerful telescopes can see it in detail. A nebula as large as the moon in apparent size is the Helix Nebula, but it still requires a phototime exposure to be seen at all. Its stunning form has inspired some people to call it the Eye of God. At about 450 light years away, it is among the closest planetary nebulas to Earth. As such, it has been studied intensely. This photo from the Hubble Space Telescope is one of the most detailed astronomical images ever made. Among the surprises it reveals are strange spoke-like knots inside the nebula.
They call them cometary knots, thinking maybe they're originally from old comets around this star, when in fact it's really a natural interaction of the starlight with the gas. As the starlight comes out, it sort of shocks the gas, kind of like throwing cold water on a hot fire, and it causes the gas to sort of curl and fragment.
The brilliant colors seen in photos of planetary nebulas are deceiving. If a spaceship were near the central star of the Helix Nebula, for instance, the glowing gas would be practically invisible because it's so thin. Only by speeding to the planetary nebula's outer reaches would the view start to change.
We would have to travel for about 1,000 solar system radii before we began to see the glow of the gases in the planetary nebula itself. And these would look a lot like the aurora that we see here on Earth. The colors would be beautiful. Then shortly after that, we would finish flying through the nebula and we would be out in the depths of space.
Looking back on the nebula, the colors are more apparent. The gas is otherwise too thin to be seen, unless we are looking through its entire envelope, billions of miles thick as we are now. But even at this point, we need help. Our eyes see the expected hydrogen red, but more colors show up, and the structure becomes clearer if our spacecraft applies the Hubble palette to our view. Still, our view of the nebula is limited by our position. Just as we do from Earth, we're seeing it from only one direction. It looks like an elongated ring, but our spacecraft speeds around the nebula, and we realize that from another angle, it looks very different. It is not a ring of gas, or even a sphere, but two distinct intersecting disks, possibly caused by the central star discharging gas in two separate phases at different times near the end of its life cycle. The questions surrounding the shapes of planetary nebulas are among the most perplexing in all of astronomy.
Let's take a look at some of the shapes of planetary nebulae. They range from round, like the Lemon Slice Nebula, to elliptical, like the Spirograph Nebula and many others, to extreme cases like the Ant Nebula and the Double Squid Nebula, otherwise known as M29.
Since a star starts out as a sphere, you might expect its dying gasp to produce a spherical planetary nebula. But in fact, only 10% of planetary nebulas have this shape. Among the engines behind more exotic forms are the stellar winds from different layers of gas thrown out by the star at different times in its death cycle and at different speeds.
And what you get is an interacting set of winds colliding with other winds from the inside. That's a process that sculpts the nebula and helps to give it its interesting shapes.
The most intriguing of the planetary nebulas are those with bipolar shapes. Mysterious forces within these strange objects cause glowing gas to shoot out in jets, reminiscent of the stellar jets from stars in the process of being born. How could two so similar phenomena happen at both the beginning and the end of stellar life?
Jets are a ubiquitous phenomenon in astronomy. What all these jets have in common is the presence of an accretion disk, which is rotating gas, magnetic fields in the rotating gas, and as material flows through the accretion disk and loads on the field lines, it gets blown back out into space.
But a dying star doesn't have a disk of material falling into it. That is, unless it's a part of a binary pair, two stars orbiting around each other. Binary pairs are very common in the universe.
As the two stars rotate around each other, one of the stars is giving up mass to the other. Material flows from one star to the other, and you form an accretion disk. Magnetic fields appear in that accretion disk, and material is blown off it, just like in the other cases as well.
Planetary nebulas represent the normal processes of star death throughout space. But there are giant stars in the universe that are far from normal. They conclude their lives in massive explosions, and often the nebulas left behind are the only clues to just how they met their violent ends. In the year 1054, a massive star blew up 6,300 light-years away from the solar system. From the Earth, it appeared as a new star, the most brilliant in the sky. 10 times brighter than Venus, it was visible in broad daylight for 29 days. It was noted by Chinese astronomers and perhaps the Anasazi of New Mexico, as seen in one of their petroglyphs. It faded away almost as quickly as it appeared, and today we can see it only through telescopes. But what's left of it is spectacular. 1,000 years later, we call it the Crab Nebula, one of a variety of nebulas known as supernova remnants.
Supernova remnants are essentially the expanding debris clouds from the stellar explosion of a really massive star. It's the death explosion of that massive star at the end of its life.
Supernova remnants are something like planetary nebulas in that each results from the death of a star.
As a star first evolves to become a planetary nebula, it ejects dense mass from its surface very slowly. This is not an explosion, it's just an ejection. A supernova is much simpler. It's just an explosion. Everything happens in seconds. And the nebula that we see around it is the shrapnel that still remains.
The light show comes from the explosion's shock wave, smashing into the surrounding material and causing it to glow. The principle was dramatically illustrated as it actually happened in 2004, when the Hubble Space Telescope caught this shock wave striking a ring of gas in the remnant of a supernova that exploded 160,000 light-years away in 1987. Closer to home, the Crab Nebula remains the most famous of all supernova remnants. Studied through telescopes for 300 years, it contains a secret buried inside, undiscovered until 1968.
At the very center is a pulsar, spinning at 30 times per second.
A pulsar is a spinning neutron star so dense that 1 teaspoon of it would weigh 1 billion tons. The one inside the Crab Nebula is just 18 miles across and weighs more than our sun. It's spinning fast, but losing energy by gradually slowing down.
And the energy of its rotation is being transferred into the gas, and in fact, much of the radiation in that nebula is powered by the slowdown of the pulsar.
That radiation is seen as the eerie blue glow in the center of the Crab Nebula. It is generated by electrons moving at near the speed of light through the magnetic fields of the pulsar. But there's more than a blue glow. Recent space photos reveal that the magnetic fields are stirring up the center of the nebula.
You see little ripples emanating out from the pulsar. It's not a bad analogy to think of magnetic fields as stretched rubber bands, and when you pluck them, you cause a disturbance that works its way through them. And that's what's going on somehow or another. The details are beyond us, but we can see the phenomenon, and it's quite clear.
The death of the star that formed the Crab Nebula is part of the life cycle of the galaxy. The gas expelled into space as supernova remnants and planetary nebulas returns to the interstellar medium, where it becomes raw material for future generations of stars.
This process cannot go on forever because we have a finite amount of hydrogen gas. Sooner or later, you use up most of the hydrogen and helium, which light up the stars, and the stars blink out.
When you look at the Milky Way today, 97% of its mass is in stars. 3% is left in gas. And as star formation proceeds, that reservoir is going to go down and down and down. Certainly, star formation will slow down because this gas is just harder to get out of the ground, as it were.
But astronomers using the Green Bank Radio Telescope have recently discovered one source of gas in a massive cloud outside the Milky Way.
The very interesting thing about this cloud, which has been called Smith's cloud, is that it's very massive. It's got about 1 million times the mass of the sun in it of gas and dust.
Well, this cloud is headed right toward the Milky Way, and in 20 to 40 million years, it's going to collide with us. Now, that's going to create a pressure, a shock wave. And it may set off a generation of hundreds of new stars when it collides with the Milky Way.
As the gas in Smith's cloud is compressed by the collision, a brand new star-forming nebula will light up the galaxy, and the life cycle of the universe will continue. In the long term, however, there aren't enough Smith's clouds to keep the process going, and nebulas